Hey y'all, Data Guy here, and today I have a video for you going through TensorFlow. TensorFlow is an open source software library which was developed by the Google Brain team that's really used for deep learning and machine learning applications. It operates kind of as a framework that's going to allow developers to construct, train, deploy neural network models efficiently. And what a neural network is a computational model which is inspired by the structure and functional aspects of biological neural network in the human brain. So it consists of many multiple interconnected units or nodes called artificial neurons, which are organized in layers. And these are able to process input data, perform simple calculations to transmit signals to other neurons. And so a typical neural network will comprise of an input layer, one or more hidden layers, and an output layer. So an input layer will receive that input data. Each neuron in the input layer represents one feature of that input data. Then the hidden layers are where the computational heavy lifting comes from. Each neuron in these layers, applies a weighted sum to its output, then has a nonlinear activation function, so a function that's going to say process the data and then send it out to another node. And so the number of hidden layers and number of neurons in each layer can really vary, which defines the complexity and capability of that neural network. Then finally, the output layer produces the output of the network. And for classification tasks, this is something like a probability of what is the probability that George Yates is a data engineer? For regression tasks, it might be, hey, what is the price of Ethereum going to be predicted to be in 2050? $1 billion, obviously. And so the connections between these are governed by associated weights, and typically are just using these to train algorithms, then use the neural network to just provide more efficient processing of all the computation that's going on within that algorithm. Now, where TensorFlow comes into play, is it just makes all this easy. So it has a comprehensive ecosystem of tools, libraries, community resources, which allow you to translate these really complex algorithms into practical applications where you don't have to necessarily set up the entire neural network. You can use TensorFlow as your backend and use that to actually define all those relationships and just define the models that you actually want those neural networks to run. So this really flexible architecture supports ton of different range of tasks, from something like that simple linear regression all the way to really complex human brain simulations. So it's applicable in fields from natural language processing, computer vision, predictive analytics, and can really process large scale data across both CPUs and GPUs. And because the neural network implicitly has support for distributed computing, it's really great solution when you need to process terabytes of data across thousands of different computers. That's why all the NVIDIA G100s are completely sold out, because they're using them for neural networks. So I just wanted to kind of give you an understanding of what's happening under the hood here. And now we'll go into my local development environment. I'll show you how to get set up with TensorFlow and build your first TensorFlow program. So here in local dev, the first thing we're going to need to do is just pip install TensorFlow. So here, run this command. And this is going to install it on my Python 3.1 environment. And this is important because that's where we're going to need to select the kernel for this Jupyter notebook. So make sure that you select the kernel that you are installing your TensorFlow library into. And obviously you're going to need to have pip, but if you don't have pip and you're working with Python, I don't know what you're doing, man. Or woman. So here, just going to let this install, and then I'll show you how to set up the notebook. So once you have pip installed, we can close terminal for now. And then what we're going to do is select our kernel. So select that Python environment, so that 3.1. So you can see here, Python 3.1.7 recommended, because that's what I normally use. And then here we are going to import TensorFlow. And it's not found, so give me a second to figure this out. So what I just had to do is just change my Python kernel. I was in the wrong one, so I just penalties of having a bunch of different Python environments installed on the same computer. But here, just make sure it's installed. Make sure you get this confirmation message here before we actually create our next code block, where we are going to load and prepare a just kind of preset data set, or pre-made TensorFlow data set. So this data set is really just a collection of different images, different data points for us to just use for kind of some basic data analysis here. So these pixel values, which are contained within these images, range from 0 to 255. So what we're going to do is scale these values by dividing them by 255. So what we'll do is create a training and testing data set where the values are all scaled between 1 and 0, and then also convert them to floating points. So here, if we run this data set, you'll see it'll download from that Google API, and pretty easy. So now that we've gotten the data in here, what we're actually going to do is use this TensorFlow Keras model, sequential model, which is going to create stacking layers where essentially you can think, hey, each layer is going to have one input tensor and one output tensor. Now, what I mean by tensor, it's really just a flat data set. It's just kind of their term for it. And so what each of these layers are first, it's going to take that input data set, it's going to flatten it to the input shape of 2828. It's going to make it more dense. So what densing is basically just creating a densely connected neural network where you have 128 neurons. That's what this is setting. And then it's using ReLU. This is the rectified linear unit, which helps the network learn non-linear relationships in this data. So after you take that, raw image file input, it's flattened to make it a simpler shape, and then we're using a dense layer of neurons to figure out, hey, what are the connections between this that it can eventually make predictions on, hey, what type of image is this? Then a dropout layer. What this does is randomly select 20% of the values and commit this layer to 0 during training, which reduces overfitting. And overfitting is where the network learns the training data too well and then performs poorly on new unseen data because it's too used to that data that it was trained on. Then finally, there's another densely connected layer, which only has 10 neurons, which normally will just correspond to the number of classes in a classification task. So if in this situation, the network is meant to classify images of digits, so because the images are turned into the raw digit code, there would be 10 classes, hence 10 neurons, because it has to have those 10 operations to predict each of those 10-digit values. So this is all in all a very simple neural network where you have an input layer that's flattening 2D data, then two densely connected layers that are actually performing those functions, and then a dropout layer that's just preventing overfitting. And so this is a really good model for image classification, which is what we're doing. So after you create the model, which should be pretty quick, then you can see it'll use it to generate predictions. So here, what this is going to do is give us an array of logits or log odd scores, which are essentially just predictive values of what the average object in this array. What are the average predictions for what an image in here would look like for each of these classes? So again, the reason because these are between 1 and 0 is because we again up here we divide them all by 255. So they're all on array, even though when you think of an image, you have 256 bytes. This is, that divided by obviously 255. And then we'll use the softmax to convert these logits to probabilities, which will actually just a measure of how likely it's going to be correct within that prediction range. So here, we'll add another piece of code after that, which is going to define a loss function. And so what the loss function does is basically take a vector of ground truth values, compares it to the vector of digits, and then returns a scalar loss for each example. And so the loss is equal to the negative log probability of the true class. So the loss is 0 if the model is sure of the correct class. It knows it'll always be correct when predicting that class. And then as that value increases, the less likely it is to actually be correct. And in this untrained model, as you can see, gives probabilities close to random. So you'll notice all these are under 10%, or almost all these under 10%. So the initial loss should be close to, if we add another block here, around 2.3. So here we got 2.1, which is just basically adding up all the different values together. So here you have your 2.1, which is now the probability. So again, not very close to probable, because again, ground truth would be 0, so 2 isn't that great. So what we'll do then is optimize it. So we're going to train and configure that model we created earlier. So we actually still haven't run the model. So here we're compiling it with our loss function, so it can actually compare and get the true probability. We're only looking for accuracy here. We're just curious about, hey, let's create the simple model. Let's see how accurate it is at predicting the output of a certain image. And then we're going to just set that optimizer to atom, which is a stochastic gradient descent method for predicting values based on the adaptive estimation of first and second order moments. This is just a really, it's essentially just taking an optimizer model class. So this is just defining the method for how we're going to do these predictive values. And then once we define that, so when you get really deep in the weeds, you'll probably be creating your own optimizers or using other ones, but this one's just super simple and computationally efficient. And what it actually looks like under the hood. So if you actually go into the TensorFlow documentation, you can see, so here, atom optimization, all the information about what's in here. It essentially has the effect of changing all these settings of the model to ones that I guess this guy Adam has figured out are the best for a computationally efficient way of just processing large amounts of data. So after we're done with that, all we can do is use the model.fit to adjust our model parameters, have it train over 5 epochs, which is just 5 iterations of training the model. So give it our training data, and then you can watch it calculate and try and learn all that data, so it can say, hey, based on this image, I expect it to have these different properties if it's a new piece of data. So here, I'll just let this train for a second and then unpause. So you can see here, based on these different accuracies, ratings, you can see it got more accurate over time as we kept training it, kept comparing its results to the past results. And so now it's 97% sure that given a new image, it can classify all the information around that image. So to evaluate it, let's feed it our testing data set. And so here, this is just, again, that data we split off earlier, and boom, it's able to predict with a 95% accuracy what each class what the classes of each image will be, what that image contains. So that's really, even though this is all numbers, this is, again, giving us information around, hey, all these different images, how likely is it to predict the accuracy of what an image contains? And then here, under the probability model, so it's, around almost 98%. Now we'll get the actual probability of it. So here, set that, and then give it our testing data. So here we're going to give it a specific piece of testing data. So this is image 5. And you can see here, it's going to give us an array of all the different values that it contains. So here you'll get a list of the different properties of an image that it predicts it to contain based on the model that we just set up and used. So don't worry if you're a little bit confused by this, because it is all TensorFlow is really advanced or really done for more advanced workflows where you need to pass it, large data sets, figure out the relationships between different pieces of data, and then give you predictive values, obviously based on that. So here, what we're doing is just really creating a simple model, figuring out how accurate it is, and then just feeding it some test data to make sure that it can generate accurate responses. And you can see kind of these reflected down here. So hope you found this useful. This was, my first time exploring TensorFlow, so apologize if I missed anything. If I did miss anything, let me know. I really am just trying to learn here and have you all learn along with me. So just want to show you how to set up and start using TensorFlow locally. I'm going to go back and do some more research, figure out some more stuff about TensorFlow. It's, it's a little bit sexier responses instead of just probability numbers. And yeah, I'll get back to you. So have a good one, y'all. Data Guy out.